Lewis structures are the most useful tool for understanding bonding in molecules. The basic idea is to form closed shell electronic configurations for the atoms taking part in building molecules. That means for hydrogen, 2 electrons, and for all the other elements, 8 electrons. This is done by electron sharing in bonds. So the Lewis structure for the element hydrogen will be shown simply as a hydrogen with 1 available electron. And so when this bonds to form H2, the Lewis structure would be written like this. But it's conventional to replace the 2 shared electrons, which now give each hydrogen a closed shell configuration, as a straight line, meaning 1 bond occupied by 2 shared electrons in that bond. So here is the Lewis structure of Cl2. Chlorine has a total of 7 electrons. 2, 3, 4, 5, 6, 7. So the resulting Lewis structure of Cl2 then, 2, 3, 4, 5, 6, 2 electrons shared in a covalent bond. So this chlorine now has a closed shell configuration, as does this second chlorine. Sometimes it's necessary to form more than 1 bond in order to give each atom its closed shell configuration. So let's take this example now of CH3, CH3. Each of the carbons has a total of 3 shared electrons with the hydrogens and 2 with this bond. So this is a correct structure. But we could discard hydrogens from the end and form this compound, CH2, CH2, in which case we would now share a total of 4 electrons between the 2 carbons, and this is shown as a double bond. We could even form this compound, in which case now we have a total of 6 electrons shared between the 2 carbons, 2 shared with the hydrogen, so we have closed shell configurations for all. Here's one more example of a Lewis structure, which is ammonia. So let's write down the nitrogen with its 5 valence electrons, the hydrogens with their 1 electron, and then this goes to NH3. So the nitrogen is now sharing 3 electrons here, leaving 2 over as the famous lone pair of which we have often talked. So let's review the rules for making Lewis structures systematically. The first step is to find the total number of valence electrons present in some compound. Let's take phosphorus trichloride as an example. We have a total of 5 valence electrons in the phosphorus, which you can find out if you go to the periodic table and see which column it sits in. We know that the chlorines each have a total of 7 valence electrons, and there are 3 of them. So this means a total of 26 valence electrons. The next step is to put the least electronegative atom at the center. Now remember, atoms get more electronegative as you go to the right of the periodic table. Rule 2 says put the phosphorus here and then distribute the chlorines around it thus. Step 3 says complete the octets for the outer elements, and so this would mean then that we would put 1, 2, 3, 4, 5, 6 electrons around each chlorine, so that together with the 2 electrons, 1 coming from the chlorine, 1 from the phosphorus, we've formed octets for the outer elements. Step 4, complete the octet for the center atom. So we have a total of 6 electrons in these 3 bonds, and that means we have to add 2 more as a lone pair on the phosphorus. Many Lewis structures can be completed this way. On the other hand, you might find structures that are ambiguous, So let me give you an example of hydrogen cyanide. And so let's put our valence electrons in on the nitrogen and try and complete an octet. So 1, 2, 3, 4, 5, 6, 7, 8. But the problem is now that the carbon is not satisfied, and the nitrogen also has too many valence electrons on it. So let's move a pair of electrons here into a bond, and let's do that again because we still have an imbalance of electrons, and we end up with this structure now. And so we have 2, 4, 6 electrons in the triple bond, and then 7, 8 completes the nitrogen with its usual lone pair, and we now have 8 electrons around the carbon, 4 in its valence states. So this is the correct Lewis structure for hydrogen cyanide, and to complete it we've used multiple bonds. Now, often it becomes necessary to distinguish between two of Lewis structures, and the deciding factor in choosing the right Lewis structure is something called formal charge. Formal charge is defined the following way. It's equal to the actual number of valence electrons in the element minus the number assigned by the Lewis structure. What is the number assigned by the Lewis structure? Well, this is all the lone pairs on that element plus a half of the bonding, or the bonds. So let's take a look at a structure that may have some ambiguity in it. Let's draw carbon dioxide. We might try it this way, by analogy with our hydrogen cyanide. So now the oxygen has an octet, the carbon has 4 valence electrons, and the oxygen can be made up to an octet like this. But to do this now, we have had to assign 1, 2, 3, 4, 5, 6, and then a half of this bond, 7 electrons to the oxygen. So the oxygen has a valence of 6 minus 7. That means the formal charge is minus 1. For this oxygen here, we have assigned 2 electrons as lone pair, a lone pair on the oxygen, and then 1, 2, 3 coming from half the electrons in the bond, that is 5. So the formal charge is 6 minus 5, and that's equal to plus 1. Now, if we look at this structure here, in which we share the bonds out equally, so now the carbon is satisfied, and the oxygen has 2, 4, 5, 6, 7, 8, 2, 4, 5, 6, 7, 8. The number of electrons on the carbon is right. On the oxygen, it's 1, 2, 3, 4, plus a half of this bond, 6, that is correct, and 6 for this. So this one has a formal charge of 0 on the atoms, and is indeed the correct structure. Finally, we turn to one additional source of bonding energy, which is a resonance structure. If you look at the way I can spread the double bonds, I can put them here, and then here, and then here, or I could put them here, and then here, and then here, which, in fact, doesn't matter. And there are therefore, in the words of Linus Pauling, 2 resonance structures that can contribute to the final structure. So the final structure is often shown with the bonds delocalized this, or more often like this, in which we show the electrons associated with the double bonds simply as a circle in the middle of the benzene ring to indicate that they are delocalized. This resonance really does add a significant stability to the molecule, as we'll see when we turn to calculate the orbitals that stabilize molecular structures.